Character locomotion represents a fundamental yet persistently challenging research problem in both computer graphics and robotics. To achieve robust and natural locomotion control, a variety of control strategies have been proposed. However, despite substantial progress, the quantitative evaluation of controller robustness remains comparatively underexplored. To address this issue, this paper proposes a benchmark framework for the quantitative evaluation of various biped locomotion controllers. Prior to the experiments, our system stores the initial pose used to restart each trial. Our benchmark framework defines push variables. To ensure reliable results, a slight perturbation was applied to the initial pose at the start of each trial. Once the settings are configured, each locomotion controller operates a simulation. The system applies external forces, defined by the push variables, to the simulated character and observes whether it fell. This process is repeated a predefined number of times. After completing all variable configurations and controller executions, we evaluated and analyzed each controller's robustness and character based on the experimental results. We included a total of 5 locomotion controllers. The first 4 are widely used and well-established methods, while the 5th is a new controller proposed in this paper. This method is developed based on insights gained from the experimental results of the former controllers. Force variables consist of 3 components: force magnitude, direction, and timing. Direction indicates where external forces are applied, spanning from 0 degrees to 360 degrees in 30 degrees increments. Timing represents when an external force is applied. We normalized it such that phase 0 marks the start of the right foot swing phase, and phase 1 the start of its support phase. When external forces are applied, the character is considered to have fallen if the height of its root joint falls below a predefined threshold. For detailed experimental results, please refer to section 5 of the manuscript. We also propose a new control method called MMIPMRL, which combines MMIPM approach with deep reinforcement learning. It generates desired footstep locations by minimizing the deviation between simulated motion and reference motion through a fixed phase-dependent displacement map. In contrast, MMIPMRL generates state-dependent footstep deviations as an action of policy instead of a fixed displacement map. For a detailed description, please refer to section 4.3 of the manuscript. The learned policy generates natural-looking locomotion and remains highly robust under external forces. With this method, we generate more natural locomotion without compromising the robustness of MMIPM. Thank you for watching.